A quick new idea daily from the world's greatest TEDx talks. I'm your host, Atosa Leone, and this is TEDx Shorts. We may not realize it, but many structures found in nature, from the microscopic organization of water molecules to the delicate composition of a spider's web, all produce sound. These vibrations and frequencies provide a design model for scientists and engineers, says Marcus Buehler. He's a McAfee Professor of Engineering at MIT, and he shares what listening to these tiny sounds can tell us about the basic building blocks of life.
Sound is a really elegant way of capturing multiple levels in the material organization. We were going from the big, large scale, and we can recognize from the beginning the architectural levels, structural details, all the way down to the molecular scales of the individual atoms that make up the amino acids, which are the building blocks of proteins. These amino acids, to proteins, to assemblies of proteins, to filaments, fibers, is a really complicated puzzle. By using sound, we can hear simultaneously all these different levels. Each level contributes a particular type of frequency spectrum. By listening to it, our ear, our brain can process the information, and we can design new hierarchical structures. If you open a chemistry textbook, most likely you're going to find a drawing of a molecule. These kind of models change over time, but I would say they're all wrong because these pictures in the textbook are static. They look like static drawings, when in fact, molecules are continuously moving. They're vibrating, they're moving all the time. These vibrations and movements is actually what defines the structure of these molecules. Each molecule has a unique fingerprint of sound. Just like you can hear the vibrations of a guitar, you can hear the vibrations creating what we call music. In a similar way, vibrations of molecules also have a unique sound, and we can make it audible by transposing the frequencies into the audible range so that our brain can process the information. What you hear here is the sounding of a complex protein structure. The protein is vibrating all the time, it's continuously moving. These movements and motions can be made into audible sound, just like playing multiple guitars, multiple instruments, and multiple structures in musical composition. By having a model of a protein in sound, we can begin to understand the protein better, have another way of understanding structure. We can very quickly process information. We can understand questions like mutations. We can understand how proteins might change their folding geometry as mutations happen. One discovery made recently is that each of the amino acids, there are 20 natural building blocks for all proteins called amino acids, have a unique sound. They have a unique fingerprint. In other words, they have a unique key on a piano. They all sound different. What you hear now is the sound of each of the 20 amino acids going from the beginning to the end. These are the sounds of life. These sounds can be utilized to build models of proteins. In fact, what you hear now is the musical representation of the spike protein of COVID-19's pathogen. Because the protein is so big and has such a complicated folding geometry, the musical composition that results from this protein to reflect its structure is very long. In fact, it's about 1 hour and 50 minutes long. The resulting music is a very complicated piece because we have many different melodies weaving into another, creating what we call in music counterpoint. Counterpoint is a concept introduced and used very heavily by Johann Sebastian Bach, for instance, a couple hundred years ago. In fact, in recent work, we have used proteins to build data sets to represent thousands and hundreds of thousands of hours of music that reflect these proteins and train artificial neural networks to listen to them. These AIs can then generate new music based on what they have learned. These new musical compositions can then, once generated, be translated back into proteins because we have a unique mapping between the protein sound and the genetic information. So we can go from protein, from material to sound through the understanding of the equivalence of waves and matter. We can then use waves or sound as a way of creating new sound, editing the sound, manipulating the sound, coming up with new design solutions, not only by human, but also using AIs. In the case of COVID-19, one of the design problems we're after, of course, is to think about ways of creating antibodies, molecules or proteins that can bind to the protein in the virus more strongly than the protein can bind to the human cell. What you hear now is one of these proteins that we have generated using AI. This is a protein that nature has not yet invented. Now, how do we create this? We listened to many different kinds of coronavirus spike proteins, different species, different evolutionary stages of the coronavirus, not only the current COVID-19, but many other coronaviruses. We then let the AI method generate new music that reflects the innate structures in these particular type of proteins, which are all spike proteins in viruses. This kind of composition, this kind of sequence might in fact hold the key to an antibody because it matches the types of sequences we find in the protein in the genetic information. Here you can hear a piano composition that reflects the moment of infection. This is a protein structure that resembles the moment when the virus spike protein attaches to the human cell. So music here provides a microscope into the world of molecular motions, into the world of infection, detachment, and the interaction of the virus, ultimately with the human body.
The TEDx talk you just listened to was recorded at a TEDx event in Boston, Massachusetts. All TEDx events are independently organized by volunteers who believe in TED's mission of ideas worth spreading. Special thanks to the organizing team at TEDx MIT. Want to listen to more TEDx talks? Visit our website at ted.com/TEDxShorts. I'm Atossa Leone. Thanks for listening, and see you tomorrow.